Hi everyone, my name is Andrew Dobis and I'm a master's student at ETH Zurich. I'm here to talk to you about exploratory work done on functional coverage-driven fuzzing for Chisel designs. This work was done along with Chark Peterson and Martin Truebel over at the Technical University of Denmark. So let's get started. So let me start by giving a brief overview of the presentation. We will first start by presenting the motivation behind this project. After that, we'll introduce the necessary background on Chisel and fuzzing. Finally, we will describe our solution for fuzzing Chisel designs and talk about our initial experiments with the fuzzer. Please remember, of course, that this solution is still very much a work in progress, so please keep that in mind throughout the presentation. Let's talk about our motivation behind this project. So the term fuzzing is often associated to software testing. But with the current move towards using software testing techniques for hardware, fuzzing is slowly being introduced to the digital design ecosystem. This means, of course, that recent work has been done on fuzzing for digital circuits. However, none of them have been focused on using hardware-centric metrics such as functional coverage to drive the fuzzing. So our goal with this project is thus to explore the effects of driving fuzzing using a metric that inherently contains data about the device under test and evaluate its impact on the fuzzer's efficiency. So before we go any further, I'll quickly present some background on Chisel and fuzzing in general. So fuzzing refers to the automated input generation driven by a certain metric. This allows for more effective randomized testing with the goal of exploring all or most interesting cases without having to go through every single possible input value. Then we have Chisel, which is a hardware construction language embedded in Scala. It allows for the high-level description of digital circuits using object-oriented and functional programming constructs. Chisel is compiled through an intermediate representation called Fertile before finally outputting Verilog code, which can be simulated using Verilog simulators such as Verilator. Finally, there's functional coverage, which is a coverage metric based around evaluating the testing progress of a specific feature of a DUT. These are defined in what's called verification plan. By these, I mean the features are defined in what's called a verification plan. Functional coverage gives a qualitative measure of the testing progress, telling us which features of the DUT have been tested. So the specific type of fuzzing we use is called coverage-driven mutation-based fuzzing. This is based around mutating a set of initial inputs called seeds, depending on the coverage results they obtain after feeding them to the DUT. So these mutated inputs the mutated inputs that generate a higher coverage percentage are added to the seeds as interesting inputs. And these are then used as a basis for further mutation. So the figure you see here gives an overview of the general fuzzing loop. So let's talk about current solutions in terms of fuzzing for digital designs. So the first here is called American Fuzzy Lab, or AFL for short, and it's a common software-specific fuzzer. AFL uses coverage as a driving metric and introduces mutation techniques which are efficient and often lead to interesting results. AFL is often used as a basis for other fuzzers, and its mutation techniques are what we use in our solution. After that, we have RFuzz, which is a fuzzer for RTL circuits. This solution leverages FPGAs to accelerate their fuzzer. They also employ techniques for fast and deterministic memory initialization. RFuzz also relies on edge coverage, which is a sort of derivative of branch coverage, as their driving metric. Finally, a completely different approach is used by fuzzing hardware like software. Here, they employ methods which translate a DUT into a software model, which is then used with standard software fuzzers. So all of these solutions have one thing in common, and that is that they rely on the same metric to guide their fuzzing. So we try to ask ourselves the following questions. One, why not use a more complex metric? And two, what will the performance impact of using that complex metric look like? So a potential answer would be to say that the performance impact would be too great. However, we think that the performance impact of using a complex metric can be recuperated by a faster converging fuzzer, meaning a fuzzer that converges in less iterations. So now let's move on to our solution, which is to create a fuzzer made specifically for Chisel designs, which uses functional coverage as a driving metric. So this fuzzer works in 5 phases. First, we interpret the input files as bit streams and load them into a queue. Then we select the next file from said queue. After that, we mutate the selected inputs. Then we run it through, we run the test on the DUT, and the outputs of the test are then compared to a golden model's outputs. And if they match, we retrieve coverage results. Otherwise, we report it as a bug. And then finally, we compare the coverage results with the previous ones, determining if the test was interesting or not. And if it was interesting, we add it to our corpus of interesting tests. So before we go any further, it's important to explain what we define as a test. The main difference with a software fuzzer test is that here we need a way of defining timing. This is done by stepping the clock between every input-sized segment in an input file. The input size is the sum of all of the DUT's input bit lengths. So for example, given a DUT with 2 32-bit inputs and 1 64-bit inputs, the input size would be 128 bits. So that's how we define a test in our fuzzer. An example is given at the very bottom for the example DUT. So now let's talk about the mutation engine. So first attempt was to directly use AFL's engine by interfacing it into the Java native interface. However, this increased the compilation time and added dependencies to the project, which we want to avoid. So a solution to that was to re-implement a subset of AFL's mutation engine in Scala and adapt it to work well within our fuzzer. The mutation engine works by running a set of deterministic, then non-deterministic mutation passes. So currently, we only implemented deterministic passes, but we are working on adding non-deterministic passes as well. Let's talk about our initial experiments. So we tested our implementation on the Liros accumulator ALU. This has 2 inputs, one 3-bit operation and an 8-bit data input, as well as a 16-bit accumulated output. Our goal here is to check every operation with the most interesting operands. To do this, we need to first create a verification plan for the functional coverage, then second, create an input seed file, and finally, run the fuzzer with the pre-existing golden model. So here for the Liros accumulator ALU, we already had a golden model for it. So if for any type of DUT you want to test, you always need a golden model to check, to compare your results to within the fuzzer. So the verification plan is defined using a set of cover constructs, which tell us which ranges of values we want to expect for each operation. Functional coverage allows us to have both coarse and fine-grained coverage information about our test, which is beneficial for the input mutation. After the verification plan is defined, we define an input seed. Here it simply computes 32 plus 25, for example. Finally, we call the fuzzer by giving it to the DUT, the coverage reporter, golden model, and then the output and seed files, file names. So yeah, these initial tests so far, however, have shown sort of non-conclusive results due to the fact that the fuzzer still only has deterministic mutation passes, and thus can't really be compared to any other fuzzer yet. So for it to be able to be compared to anything, we need to also have non-deterministic mutation passes. So work is currently being done on also enabling the use of edge coverage on our fuzzer so that we are able to easily compare it with the functional coverage counterpart. But we expect that functional coverage will lead to a faster converging fuzzer. However, the low efficiency of our current functional coverage implementation still leaves a lot of room for improvement. In conclusion, the paper we presented is a sketch of how to support testing and verification of digital designs described in Chisel with fuzzing driven by a hardware-centric metric. It's also a basis for a more detailed performance evaluation when all of the mutation techniques have been added. So current work is also being done on extending these fuzzing methods for constrained random code generation. So yeah, here are the references for the fuzzers I talked about. And this fuzzer is actually part of the ChiselVerify project, which you can find on GitHub. It's all open source. So thank you very much for listening. And now, are there any questions?